So we have one more class of function that we need to be able to differentiate. And this is one that maybe you haven't heard of before, right? They're the so-called hyperbolic trigonometric functions, or usually it's just hyperbolic trig functions. So I'm going to start off just defining them, right? We're not going to go into a lot of detail about the specifics of the functions themselves or their applications. Really, we're just going to focus on differentiating them. So before we do that, right, let's start with the functions themselves. The hyperbolic cosine, and it's this first one. This is the hyperbolic cosine, is defined to be e to the x plus e to the minus x divided by 2. And the hyperbolic sine over here, you notice very, very similar. The only difference is this one is subtracting where the cosine is adding. Now, I don't want to go into a lot of detail about the graphs, like I said, about the properties of these things. We'll actually circle back to that. We're going to talk a lot about graphing functions in the next chapter in the course. But for now, I do want to give you some idea of what these look like. Right, the hyperbolic sine on the right, the hyperbolic cosine on the left. And just give you a very brief idea of where these things come into practical use. If you take a wire and you hang it, right, you suspend it between two poles, right? So you think electrical poles, for example. I've got an electrical pole, and you hang a wire between them, right? The shape of the curve that wire makes can be described using this hyperbolic cosine function. Okay, so there are 4 more of these, and they're all defined in a very predictable way. The hyperbolic tangent is the hyperbolic sine divided by the hyperbolic cosine, and the hyperbolic cotangent is 1 divided by the hyperbolic tangent. And finally, we have the hyperbolic secant and cosecant, and they're all defined exactly the same way. These last 4, they're all defined in exactly the same way as their corresponding kind of regular trig functions are defined. All right, so what I want to focus on right here in this class is the derivatives of these functions. And we can find these simply enough, right? If I want to find the derivative of the hyperbolic cosine, right, that's the derivative of the right-hand side. And I'm just going to split this up, right? I'm going to make this the derivative of e to the x over 2 plus the derivative of e to the minus x over 2. And that is e to the x over 2 minus, it's a chain rule here, e to the minus x over 2. And then I can combine these, right, because the denominators are the same. This is e to the x minus e to the minus x over 2, which is the hyperbolic sine of x. Okay, and try the, go ahead and pause if you like. Try the other one real quick. Try differentiating that hyperbolic sine. Then we can do it together. All right, so I'm going to use the same approach. The derivative of the hyperbolic sine is the derivative of e to the x over 2 plus the derivative of, minus, right? Minus e to the minus x over 2. So that's e to the x over 2 minus, and again, chain rule again here, right? Minus e to the minus x over 2, which is e to the x over 2 plus e to the minus x over 2. And I can combine these together again, right, because the denominators are the same. This is e to the x plus e to the minus x, which is the hyperbolic cosine of x. So you notice this is where these hyperbolic trig functions get a little annoying. Their derivatives are the same as for their corresponding regular trig functions, except the signs can be different. Right? When we're talking about regular trig functions, the derivative of the cosine is minus the derivative of the sine. Here it's the positive derivative of the hyperbolic sine. Okay, and I have the others here, and I've written them all out for you. You can go ahead and try deriving these on your own, right? Good practice, applying a lot of the derivative formulas that we've been talking about here. And if you're following along on the website, you'll see more of this going on in the practice questions there. And again, like I said, they really mirror the regular trig functions, except the plus and minus signs can be different. Okay, so let's walk through one here so you can see, because you notice I've used this same du dx notation that I used when I was talking about the derivative of the inverse trig functions. And the idea here is, what if we have the hyperbolic cosine of some function instead of just x? Well, let's take a look at an example here. Right, I want to take the derivative of this thing. Right, what is f prime of x? Well, this is a chain rule situation, right? X squared plus x is the u in my formula. And the formula says the derivative of the hyperbolic tangent of u is secant squared u times du dx. Well, if my u is x squared plus x, that means the derivative of the hyperbolic tangent of x squared plus x is secant squared x squared plus x times the derivative of x squared plus x, which is what? Just 2x plus 1, right? So this is 2x plus 1 times secant squared x squared plus x. And that's it. Right, there's the derivative of my function. Okay, so where are we going next? We're almost done with kind of our explorations in differentiation. We have one more scenario where we needed to think about. And it's not going to be formula driven, like I know a lot of the stuff we've been doing for the last several lectures has been. Instead, the question I want to answer is, what if y is not necessarily a function of x? Right? What if y is not a function of x? For example, what if I have something like this? X squared plus y squared equals 1. That's a unit circle. Right? Well, if you pick a point on that unit circle, it has a rate of change at that point. It has a tangent line at that point, so that we can talk about the slope of the tangent line. How can we find that in a situation like this where we can't easily, if at all, solve the equation for y?